And I'll write it differently. I'll just write it as minus mu minus alpha. I'll put a t there. Well, right. And that definitely looks like that. All right. Okay. All right. So I want to do the same thing I did with the linear systems context. I want to look at the value function for the fluid model, and then argue that it approximates the value function for the stochastic model. I'm not going to prove anything. I'm just going to illustrate this, and we'll go and examine it later on. And this probably not till mid-February or something, but I just want to give you a preview. So the value function here is that, and the minimum over u, well, I already assumed the input here. If you'd like to, we could put in a little u there. Basically, well, ut is between 0 and 1. Something like that. Or put it in front of the, I'm sorry, excuse me, it's a mistake there. Because over here, we're only able to control the service. We can't cut off arrivals. All right. But of course we know the answer, u is 1, so why bother keeping it in there? It's just that there is a Bellman equation you could write down and all of that, and we know the solution, and it's given by that. And remember, c of x equals x. But that's what I'm assuming over here. And so I'm going to take my cost function to just be c of x equals x. So what is j star of x? Anybody remember their advanced calculus? So this is the integral of qt, right? And there's qt. So it looks like a very complex trigonometric formula we'll have to use to get the area under a triangle. It's one half the base times the height. All right. So, given the fact that we're drifting downwards here, once again, given that fact, I'll put a star there to just emphasize this. Given the fact that the slope here is mu minus alpha, the time that you reach the origin, you can work it out, is just your initial point divided by mu minus alpha. So you can just work that out yourself. All right. And so you could just see the first. We can compute this, right? You can compute that differential equation. I'm sure you can, and you can find the first time it hits the origin. And the first time it hits the origin is q0 over mu minus alpha, right? So 1/2 the base times the height. With q0 equals x is 1/2 times x squared over mu minus alpha. And that's it. So there's the fluid value function. Okay, cool. All right, so then you can go to the stochastic. So the stochastic Bellman equation, actually, hold on a second. No, let's do let's write down the Bellman equation. Let's do it. Before I go on. So Bellman's principle here continuous time, it's exactly the same. I pick an intermediate point in this integral, and I integrate only up to some intermediate point, and then look at the cost to go. Let's make it lowercase. Stare at this for a minute. Does it make sense to you? So I'm sneaking in a little input here, you know, where each u of t is between 0 and 1. You know, don't you all agree this is a natural analog of that discrete system, right? Over there, I should have said it out loud. Oh, yes, I did. Yeah, u equals, it was written down here somewhere. U is 1 if I'm working, it's 0 if I'm idling. I did say that. And here you just relax that and make it between 0 and 1. So I'm allowed to work 50%. So when I'm looking at this is actually a continuous time process, deterministic, on the interval 0 to t, taking values between 0 and 1. Right? So I'm minimizing the cost up to time t, and then the cost to go. So it's exactly the continuous time analog of what we wrote down before. Does it make sense? Yeah. Okay, so that's the definition of Bellman's principle. You know, and it's something it's rarely ever proven because you just say, well, it's obvious, isn't it? Because it's just a repetition of the fact that once you get to qt, you know that you're going to follow the optimal path from then on, and that will be the cost to go. It's just a definitions almost. But you can fool around with this, and I'm going to do it. You can sort of plug in the optimizer and shuffle things around. I'm deriving some stuff for you. 0 equals the integral from 0 to t of c of q star plus j star of q star and let's divide by t. All right. I just want to show you how easy deterministic optimal control is. You know, I claim that if you think about this long enough, you'll see it's really nothing. You know, and then if an optimal solution exists, optimal Q exists, well, we know it does in this example. You just make U 1. You plug in that optimal Q, with the start. Well, Q0 is given. You plug in the optimal input. You get the optimal state process and all that. And you see why I'm doing this, right? Why I'm divided by t. If I'm going to get make big T, this is for any t. Right away, we know this is differentiable. You know, because this is definitely going to have a limit as t goes to 0, and therefore this has a limit as t goes to 0. So you take the limits, and you get 0 is equal to, well, as capital T goes to 0, that's just c at the initial point. And then here, that's the derivative. And actually, you all remember the chain rule, right? you get this thing. All right. Oh man, what can I kill? I can kill that. Okay, so I'm going to take one more step and we'll go to the stochastic case. Now, when I went from here to here, I threw away a lot because I had a minimum here and I just threw it away and I got this equation, which is true, but if I'd kept that minimum a little longer, I'd get something a lot stronger. You know, I mean, I've got Q dot is equal to some function of Q and U. That's what this is. It's a pretty boring function of the input U, and there's no Q in this case. It's actually only a function of U, but in general it'd be a function of Q as well. And the real equation that you normally would get, it's called the HJB equation. It's what you'd get is if I kept that minimum here, you know, if I just kept it and kept it going along. And what you get is a minimum over U. And suppose we had a cost on U as well. We could. And I've got a grad J star. And I've got a Q dot. But Q dot is just a function of Q and U. And that's equal to 0. So I don't expect you to have seen that before, but I wanted to sort of blast through it in this example so you could believe that it's likely to be true. All right? And I've actually prepared some notes for you. So if you really care about this, I've got like a 2-page notes that explains it in a little bit more detail. We don't need this, but I want you to see it. Okay? So that's a continuous time version of our Bellman equation that we had before. Okay, so what about the stochastic case? So again, C of x equals x. I'll write down the same sort of equation I had before. There's an eta star plus 8 star of x equals a minimum over u. And so there would be a C of xu, but it's just x, you know. And then plus the expectation of 8 star of x at one time in the future, given x equals x. Like that. So, you know, that's, did I leave out the, no I didn't. Did I leave out the U before? I don't know. I have to go back to make sure I didn't leave out the U. I didn't, okay, cool. So that's the Bellman equation, the stochastic case. And, you know, eta star is some funky thing. What do you think 8 star is? Well, how would you ever have any intuition? There's no way you could guess. But it turns out it's almost J star. It's almost exactly that. It turns out that 8 star of x is equal to J star of x plus something small, relatively small. And I'll be more precise, it's that. And what am I missing? I'm missing an x. Right? So there is a difference between the stochastic and the fluid solutions in this case, but it's a very small difference compared to this, right? And if I had something more exotic over here, suppose that A was, you know, maybe had a Poisson distribution or some funky distribution, I would just have a constant there. So it's a very universal result. You know, I could give you all sorts of cues, mess around with the statistic here all you want, and I will get the fluid value function over there, the x squared over mu minus alpha times a half, plus a correction term which is always linear. That's true for cues, always as well. Right? And so it sounds like I'm trying to say, don't bother looking at stochastics. And not only that, remember I said the minimizer over u gives you the policy? If I replaced 8 star by j star is another monotone function, you know, and I would get the same policy. So if I pretended this was the value function, the proper value, the relative value function, it's called the, forget it. 8 star is called the relative value function. I'll make that, I'll put that in writing next month. If I pretended that fluid value function was the right thing, and I perform this minimization, this doesn't matter because it doesn't depend on u, because this is a monotone function of x, it's increasing in x, when I perform this minimization, I will get u is 1 all the time. So I get the exact right policy. Policy is independent of the statistics in that sense. I mean, it just is. So we get really, really nice solidarity. So So one thing is the policy could just be obtained from the fluid value function. You know, what we got there was what we got there. But of course, this cost, this eta star, so that's the message that I want to try to develop in this course, that performance is sensitive to statistics. If I double the variance of, instead of A just being 1 or 0, if I allow it to have high variance, then eta star will be large. So there's lots of sensitivity with respect to performance. But in terms of the policies, it's amazingly insensitive to disturbances. And we'll see that is true in a lot of cases. All right, so we did a lot in this hour. I mean, basically I crammed through a review of dynamic programming in 15 minutes. You know, I gave you, the solidarity between stochastic and fluid models for LQR and LQG and all that. And this sort of principle that, again, I want to develop over the month of February. You know, that basically we often see something like this, which is really useful. Yeah.
Right here, when you have u not equals u, you're saying that's your initial input u?
No, oh yeah, well that's right. If this is x1, then that's 0, right? I could have made that an 11. Let's do that. And then
that wasn't there earlier when you first
did I forget to put that in? I forgot to put the input in. I thought I might have dropped it. It's possible I dropped it. No, I have to condition on both. I mean, that was an omission. I have to condition on what's the initial input state and what's the initial input.
Eta star would always have that information.
No, I mean the Bellman equation has that. So, did everyone notice I changed the 0 to 10 and I made that an 11, just to emphasize again the time homogeneous dynamics. But I forgot to put in the u in the linear case, and so it should have been there. And by the way, I've got all of this in really careful typed notes, and I will share those with you tonight or tomorrow. Okay, I've got every single bit of these slides is in this whiteboard's in careful notes, including this.
Here you derived it with respect to t.
Yeah.
I didn't see that show up.
Oh, no, right here. No, it's because the derivative with respect to time is given right there. Yeah. So I just substituted in that we have dynamics here. So I generalized things. I said more generally, suppose that we had, this is sort of ugly to write down. you know? So this is just some function, in this case just a function of u. And generally it'll have u and the state as well. So if you had some function like that, then this is a Bellman equation. And the reason is again, because f is just q dot. Is that answer? Right. Yeah. I'm using the fact that we have an expression for q dot. Yeah. Okay. Yeah. Yeah. All right. All right. So. Cool. And do I do it or not? I think I wait on this. So I actually thought about saying a few things in advance about what are the ingredients in part 3 of the course, but I think it's more valuable to postpone that. I'm going to go in and start to move my way into the Markov material. Anybody want a break? 2 hours. 2 hours. I think we should take a break. Okay, so let's take a 5-minute break and then we'll start.